This is the work that we've been doing on a Jamin Interferometer for high temperature piezoelectric measurements. We'll see some other interferometry measurements in some of the other talks. These systems, they're complementary. So our system at MPL is intended to be capable of measurements up to 1,000. There are some issues with actually achieving measurements of 1,000, but the system is capable of that. And it's a DC measurement, so we can include thermal expansion. The other systems have different attributes and different temperature ranges, and by comparing the results from these different systems, we're able to grow our understanding of the measurement process. Most of this work was done by Peter Williams and Alex Bloomfield at MPL. Okay, the outline of the talk, I'll just describe briefly the principle of the interferometer, some of the experimental details, how it's set up for doing high temperature measurements. Then we'll have a look at some of the results, and again I'll go over, again in this, we're still in the initial stages of the uncertainty analysis for this system, and then the conclusions. Okay, so the interferometry in general, we have a laser source. The laser source is split by a beam splitter. One path goes to a fixed reference. The other path goes to the sample, which in this case is the piezoelectric sample. The beams are reflected from those two mirrors. They're recombined at the beam splitter, and the combined beam goes into the detector. If those two beams are in phase, optically in phase, then they will add, and we'll see a large signal. If the two beams are out of phase, then they'll cancel, and we'll see a very small signal. So depending on whereabouts this moving sample is, we will see a variation in the phase, and we'll see change from high intensity to low intensity at the detector. Okay, so I'll just written down some of the advantages of interferometry. There are other ways, of course, of measuring the movement of a piezoelectric, but some of the reasons for doing it using interferometry are that it's a non-contact method, it's an optical method, so we don't have to bring measurement probes into contact with it. As far as the actual optical access is concerned, then there are no issues around temperature. The laser beam doesn't melt or evaporate. It's capable of doing DC measurements, but it's also capable of operating at higher frequency. We've done quite a bit of measurements on piezoelectric expansion using a dilatometer, which is fine for very, very low frequency measurements, but it won't take you above fractions of a hertz, really. And being an optical method, then it gives us a route to making accurate and traceable measurements without the need for reference. Even a dilatometer, you really need a reference material to calibrate it, but in principle, we're measuring wavelengths of light, so we should be able to do this without a reference material. And one of the things that we would like to think about within this project is the possibility of reference materials for piezoelectric measurements, and they would need to be calibrated in some way. Okay, so this particular interferometer is a Jamin Interferometer, and there's a complicated diagram here, so I've drawn this out in a simplified version. We have the laser source, we have the beam splitter, and this produces two beams. One is the reference beam, and one is the sample beam, as in the simplified diagram I showed previously. But what's happening here is that the reference beam makes two passes onto the sample, onto the reference block, and the measurement beam again makes 2 passes onto the sample. And the reason for that is that corrects for any tilt in the position of the reference block. And in the heart of it is this polarizing beam splitter, and after going through basically that path, then we end up with 2 interferogram signals which go to the detectors. And the reason there are 2 of them is they've been optically set to be 90 degrees apart, and so we get a sine signal and a cosine signal. These 2 signals look like this. So as I said before, as the sample expands, then we see a variation in the intensity. We see fringes, interference fringes, and these 2 signals are exactly 90 degrees apart. So we get a sine signal and a cosine signal, and the tangent of the angle, the phase angle, is the ratio of those 2. So it makes it easier to take out some of the influences of beam intensity, for instance, and also from an accuracy of measurement point of view, you can see that when we're at the top of the sine signal, it's a flat top. The measurement is very insensitive, but we're at the maximum sensitivity of the cosine signal. So wherever we are in that phase angle, we get a good sensitivity out of the instrument. Tim referred to some of the aspects earlier of the design of the sample, and we've designed these samples really so that we can use them in different measurement setups. And Guido Barkel later will describe the setup of PTB, which has very, very high requirements for flatness and parallelism of the sample. Our requirements are not quite so stringent, but they still do need to be quite flat and quite parallel. So these are polished and electroded samples, and these are the sample specifications here. So at the moment, for the purposes of the comparisons, we're working with a fixed sample dimension. These 15mm discs, 2mm thick, and they're polished to a high specification of flatness and parallelism. One of the things that we're looking at the moment, this sample requirement means that samples essentially have to be prepared especially for doing this measurement. We're looking at adapting the system to give us much more versatility over the sample size and aspect ratio, and we can do that by cutting out some of the beams in the interferometer, which gives much more versatility, but we think we will only be able to do this for AC measurements, so we'll lose the DC part of it. Okay, so just some details on the furnace. The furnace will operate up to 1000 degrees C. It's a 3-zone design, so it gives us a good uniformity and stability of temperature. There's a large, I think it's 80mm window in the top of the furnace, so we've got good optical access into the furnace, and it operates. It can operate under air or vacuum, but the interferometry is for the interferometry we've been operating mostly in vacuum. So here's just a photograph of the elements in the system, and a closer view of the furnace tube, and the sample area is in the bottom here, underneath that flange. Oh no, sorry, it's upside down. The sample is here. So this is all. It's actually the other way up. The sample is at the bottom of the furnace. Okay, so we've because it's the analysis that we have to do and the data manipulation of the interferometer signals, then this has to be computer controlled. So we need very fast data acquisition on the interferometer signals for doing expansion measurements. I mentioned here, if we look at these fringes, as we go from one cycle to another, the phase angle goes from 0 up to 2 pi, 0 to 2 pi. So just measuring phase angle doesn't give us the total expansion. So we need to track that phase angle as it goes around these circles and count the number of fringes. So to do that, we need to have very fast data acquisition to make sure we don't miss any jumps or changes in the phase angle. Okay, and this is the sine and cosine signals I described earlier on the screen. Okay, samples. Like Tim said earlier, we've had getting samples with stable contacts has been challenging, and now we are able to get reflective surfaces. It's doubly challenging because it doesn't, for the interferometer, it's not enough if it's just conductive, it has to be reflective as well. But now we're getting stable measurements up to 500 or 600 degrees Celsius. Okay, and there are, as you can imagine, quite a number of complexities to getting the interferometer to work reliably. We've got quite long beam paths through the furnace, so the overall alignment is important. It's that setup that I described, which takes out tilt, and the fact that we're measuring the differential path between the reference surface and the sample surface means that it is quite insensitive to vibration, but there is still an effect there. And some things like flexure of the window under vacuum, all these things need to be taken into account. Okay, so another thing which you need to be aware of when we're operating in vacuum is that low levels of vacuum, with poor vacuum, you can get breakdown between the electrode faces. As we reduce the pressure, then the breakdown strength drops initially, and then at very low pressures it starts to increase. So we need to make sure that we're operating on with sufficient vacuum to prevent breakdown effects. And this just shows, this is just some thermocouple measurements showing the temperature stability within the furnace. So as far as the thermocouple measurements are concerned, we are getting quite good stable temperature. Another thing that you have to do with this type of interferometer is apply something called a Heydemann correction. When we measure these circles, the sine and cosine circles, then ideally they will be perfect circles, but they never are for a number of reasons. They're always some form of ellipse, and this Heydemann correction measures the shape of the circle, applies a correction to bring it back to a perfect circle, and to centre that circle around 0. And if we don't do that, then we see, as you can see here, this is a piezoelectric measurement, voltage against displacement. We see this waviness in the output, which is an artifact. When we correct for it, then that disappears. Now that's not easy to do when we're trying to measure across a wide temperature range. You'd normally do this by putting in some deliberate path length modifications so that you can measure that ellipse, you apply your calibration, and you leave it like that. But because it's changing with temperature, then that becomes more complicated. The other thing that we're doing, because there are fluctuations in the measurement, it's a vacuum, so we don't have air fluctuations in the vacuum, of course, but in the region at between the furnace and the interferometer head, then there's the possibility of some convection there. So we do see some fluctuations in the measurement, and there's also, as ever, some noise in these measurements. So we're using a loop averaging technique to remove those noise effects. And you can see the effect on the noise. This is just room temperature piezoelectric measurement, so it's taking out some of the noise in the signal. But at higher temperatures, then the signal very quickly becomes buried in a mass of fluctuating signals. But when we do the averaging over a number of loops, then we start to recover a reasonable measurement of the piezoelectric expansion. Okay, this is just showing the sine and cosine loop as we're increasing the temperature. So you can see the temperature going up here, and this is with an on-the-fly correction applied to that circle. And we can see that it's reasonably consistent, and it's staying as a circle all the way over that temperature range. We can count as we go around the circle. We're tracking it and we're counting the number of times and the partial loop to give us the expansion. So that's the thermal expansion measurement. This is what it's looked like to start with. It's just going all over the place. But by tracking that expansion on the fly, we're able to get good thermal expansion measurements. So here's some of the results for thermal expansion, and the top curve. This graph here is showing the thermal expansion of a PZT sample, and the top curve is the first heating run, and the second curve is the second heating run. So it's been heated up, we're measuring it during the heating, cooled down, heated again. And we can see very, very nicely here in this first run, the negative. This is in the longitudinal direction, in the 3-3 direction of the sample. We see this negative thermal expansion, which is associated with the depoling of the material. As the polarization decreases up to the Curie temperature, then the material actually shrinks through piezoelectric coupling to the random polarization. And then above the Curie temperature, the green line takes off and we see something more like a normal thermal expansion. On the second run, the material is already depoled, so we don't see that negative thermal expansion. We see an overall positive expansion, and because the offset in these is arbitrary, we've adjusted it to meet at this point. But you can see that it follows the same thermal expansion above the Curie temperature on the second run. Like I said earlier, because it's an optical measurement, then we shouldn't need reference material to calibrate against, but we've checked it here against a silicon reference material, and we can see that the measurement is quite close to the expected expansion of silicon. So this gives us a good degree of confidence in the thermal expansion measurement. Okay, these are I've shown a few of these loops, but these just show a range of thermal expansion, piezoelectric expansions. So these are piezoelectric loops at different temperatures. So 80 degrees C is the blue one, so progressively higher temperatures, 101 degrees, 120 degrees, 140 and 163. These are not going to very high temperatures at the moment because we took these measurements for comparison with some of the other measurements. Okay, so the measurement uncertainty. So again, we go through the same approach as we did for the resonance. We're not as far along the path with the interferometer, and these things generally go through a loop. If you do an initial assessment based on a simplified model, then that will show you where some of the things that you need to fill in and build in more complexity into the uncertainty analysis to get a reasonable result. So we're taking exactly the same approach according to the GUM, and this is a simplified model of the measurement system. So again, we can calculate the phase of the interferometer signal as a function of the path lengths, the optical path lengths through different regions of the furnace. This bit here is the difference between the sample and the reference block, which is the piezelectric expansion that we're interested in. And that length we can equate to the measured sine and cosine signals, the wavelength of the light, and the refractive index of the different paths through which the light goes. And what we've done so far, and like I say, it is in the initial stages of this work, so I don't have results for this yet. But what we've found is that this analysis breaks down into two main components really. One is uncertainties in the optical path lengths. So the vacuum regions are okay, but we have to go through a window, and we have to go through a small region of air, and they can add significantly to the uncertainties. And the other part of the uncertainties is the Heydemann correction. These loops, the sine-cosine loops, are not perfect circles, and we have to apply a correction. That correction is never perfect, and that will introduce some uncertainties into the measurement. Okay, so if I could just conclude this talk, then interferometry it provides a non-contact and very direct and traceable method for evaluation of piezoelectric properties. It gives us the possibility of doing DC, so thermal expansion measurements, at the same time as the piezoelectric expansion, and there's some quite interesting behaviour in the coupling between the two. We've demonstrated piezoelectric and thermal expansion measurements so far up to around 500 degrees C, and we can see some interesting things going on, like negative thermal expansion in the poled ceramic. We're just making the first steps towards the uncertainty evaluation, and so that will really give us a measure of how confident we can be in the results and how they compare to other methods. And we'd like to see this supporting the development of reference materials. We need something like an interferometric method to support a reference material. Okay, thank you.